All right, guys. So now we're really going to hit these HR diagrams, right? I want us to really, really look at these a little bit deeper, right? I want us to understand what's going on in each of these situations and really be able to understand these HR diagrams so that we can discuss them in depth, okay? Now, some of this we talked about already, right? We've got this idea of the main sequence. You've got about 90% of stars that are here on the main sequence, okay? We've got about 1% of the stars that are up here that are these super, super cool, bright stars. And then we've got the other 9% or so. You know, you've got others, but I mean, we're talking about generalizations here. About 9% that are these cool, not cool, they're hot, but they're quite dim. They're called white dwarfs because they're very, very hot, but they're very, very small, which means they're not very luminous, all right? Now, again, I'd like for us to take just a minute. Why would a star become a red giant? Okay, why? We talked a little bit about how we know it's got to be big because it's cool and yet it's very luminous, which means the only way we can get there is by having it be very, very large, because remember, luminosity is equal to sigma A T to the fourth. So if temperature is low but luminosity is big, that means the area's got to be huge, right? So why would a star become a red giant? Well, this is what happens. At some point, if you have your main sequence star, which is mostly burning hydrogen into helium, right? And I showed you that fusion process in the previous video, hydrogen turning into helium, right? At some point, most of that hydrogen is going to get used up. We talked about the idea that the gravitation pressure, right? Gravity pulling in and the radiation pressure pushing out have to be equal. Now, if we use up most of our hydrogen and this fusion process kind of stops, then what's going to happen? Well, there's not going to be enough radiation pressure to hold it out. So the star, this main sequence star, is actually going to start falling in, right? But when it falls in, that potential energy is now turning to kinetic energy, and kinetic energy is proportional to temperature. So what happens? So the fusion starts to slow down because this hydrogen is getting used up. It's not all used up, but it's getting used up, right? It's almost used up, and so the star starts to collapse. Now, when the star collapses, potential turns into kinetic, temperature goes up, and if the temperature goes up, then now there's enough energy to start fusing the helium, right? You start to get more energy, and not just that, but the hydrogen that was in the outer layers of the star. Remember, we talked about before, we had the star, and then we had this photosphere, the gases around it. So multiple things are happening. We're starting to allow the helium to start to fuse. We're starting to, because of the extra heat generated as those gases fall inward, right, we start to get enough heat that the stuff on the outside can burn. And so it's not just the stuff in the middle anymore, but that whole photosphere, everything is burning now, right? Most of the hydrogen is used up, so there's not a lot of hydrogen. There is still some, but that's why it's not so hot, because the gas isn't super dense on the outside here, right? It's this photosphere, which is somewhat not dense, right? It's pretty thin, okay? Yes, the helium will continue to fuse and burn on the inside, but on the outside, it's mostly just that hydrogen. And again, we can tell this from the emission spectra and things like that, but it's on the outside is burning, and that's why we have a much, much, much larger star, is because the stuff on the outside now, the hydrogen in those outer levels can now fuse. And again, once the stuff on the outside fuses, we have more energy. The more energy, again, allows us to expand because of the radiation pressure. So a lot of things going into creating that larger red giant, okay? But the most part, the biggest thing to recognize is that the helium starts to, there we go. So helium starts to, the hydrogen stops happening, the star collapses, temperature increases, that then allows the outer levels of hydrogen to start burning, helium starts burning on the inside. Because of all the new energy, then causes the star, the radiation pressure to increase, the star expands, and so therefore we have these very light outer layers, not dense, very, very what's the opposite of dense? Very loose areas of hydrogen that then are allowed to burn, but at a very cool temperature because they are so spread out. All right, so that's the idea behind a red giant. All right, star starts. Ooh, what just happened? Some questions for you. Which has greater luminosity, a red giant or the sun? Well, look at your HR diagram. We see the sun down here. We see the red giant up here. A red giant, so red giant would be this one right here. And you can tell that a red giant is maybe 100 times more luminous than the sun. Easy one to start with, right? How about this one? How big is the yellow supergiant compared to our sun? Now we're talking about size, right? How are we going to do size? Well, remember from earlier, luminosity is proportional to m to the 3.5. So, if I take the luminosity of the yellow supergiant divided by the luminosity of our sun, which then should be equal to the mass of the supergiant to the 3.5 over the mass of our sun to the 3.5. Well, I know this right here because I can get that. Let's see, we're doing a yellow supergiant, so that's this guy right here. So that's somewhere larger than 10 to the 4th. So 10 to the 4th is 10,000. So this is probably not, this is a logarithmic scale. We can go ahead and say maybe 100,000, 10 to the 5th, close enough. All right, so we'll say it's about 100,000 right there for our luminosity. Okay, so that means this is 100,000 is the luminosity of the supergiant to the luminosity of the sun. And now it would be the mass of the sun, mass of the supergiant over the mass of our sun, all that to the 3.5 power. Do the 3.5 root of both sides, and what do you get? You get that the mass of the supergiant to the mass of our sun is approximately 27 times bigger. All right? So there you go. All right, let's go on next. What's going on next? All right, this is a little bit more in-depth picture. It's still an HR diagram. Notice these classifications that I mentioned before that you aren't really going to be tested on. They're down there just because it's from an old textbook, but I wanted you to kind of see what another type of HR diagram would look like. All right, main sequence stars is, again, here's our main sequence stars. They're all going down the middle. Again, main sequence means basically that hydrogen is being fused into helium using the process that we talked about in the previous one. So what's the main difference between each of these main sequence stars, right? What makes, if they're all burning the same stuff, what's the difference? Well, this is T over L, right? This is the temperature and the luminosity. Those things are different because of what we talked about before, which is mass, right? Whatever their mass is, that's going to affect where they are on this main sequence, right? We talked about Vega, that Vega is much, much larger than the sun. That was one of our discussions in a previous video, that Vega was burning much, much hotter. Why was Vega burning hotter? Well, Vega has more mass. More mass means more gravity. More gravity means to have an equilibrium, it has to have that radiation pressure, right? So in order to have the radiation pressure pushing outwards, it has to be burning hotter. So Vega is burning hotter, therefore it's more luminous. Why is it more luminous? Because it has more mass. All right? Notice this HR diagram is interesting. It has the radiuses on here, right? Anything along this has approximately the same radius to our sun. one radius. Again, we have this symbol for the sun there, right? These things are 10 times smaller than the sun. These are 10 times larger. So a lot of these main sequence stars are actually pretty close, within one order of magnitude of the sun itself. So the sizes aren't really that big. What's the difference? It's the mass. The mass is going to be the thing that's causing a huge difference as far as what the star looks like and how it burns and all those other things. All right? Can you use the HR diagram and understanding mass luminosity to estimate the ratio of the density of Altair to that of the sun? Okay, so we've got Altair right here, and we've got the sun right here. So can you compare the ratio of the density of Altair to that of the sun? I'll give you a minute to think about it, and then you can check my answers. Please pause the video now. Ding, 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 ba-ding. Here's what I got. So here's what I said. I said, well, the sun and Altair have about the same radius. All right, I can see that on my HR diagram here. Now, if they have the same radius, then they have about the same volume, right? So now, if I'm looking at density, remember, is mass over volume. So I've already said that the volumes are about the same, so now really all I need is the mass. And mass I know is proportional to luminosity. So I did a luminosity, I did a ratio, luminosity of Altair to the luminosity of the sun equals mass of Altair to the 3.5 over the mass of the sun to the 3.5. Now that I'm going to get, because I've got the luminosity, the luminosity of the sun, of course, is 1. Luminosity of Altair is somewhere over here, somewhere between 10 and 100, depending on how we read the logarithmic scale there. Just estimate as best you can. Anything between 30 and 40 is probably okay. Know that the numbers get closer together as we get higher up, so it's probably not going to be 50. It looks like it's kind of in the middle. It's probably not 50. It's probably a little bit lower. 30 or 40 is probably a good answer. Take the 3.5 root, which gives me that the mass of Altair to the mass of the sun is that the mass of Altair is 3 times greater. Now, if the mass is 3 times greater and the volume is the same, that must mean that the density of Altair is about 3 times greater than the density of the sun. All right? Now, how big exactly is a supergiant? Well, we've talked about we talked about in general just kind of what a supergiant is and what it looks like. Here's a visual idea. This is VY Canis Majoris, which is a red supergiant. Notice that this star takes up our whole solar system, all the way out to Saturn. Okay, it doesn't include anything outside of that. Okay, it doesn't include Neptune or Uranus or the Kuiper Belt, but it does include the rest of our solar system. That's how big these red supergiants is, at least how big we think they are based on all the physics that we're able to put together and understand. Okay, so these things are quite large. All right, just to give you a little bit of perspective. Okay, now I want you to think through, how does a star begin? All right? Remember, a star begins when we have this nebula, right? Nebula is made up of gas. We have all this gas that's just kind of floating around. That gas has gravity. The particles start to pull each other together. And if you're in HL, we'll talk a little bit more about this in depth later, the Jeans criterion, what exactly has to happen in order for this to actually be able to happen, right? So what's happening? These particles are all attracting each other, right? They've got a certain amount of gravitational potential energy, but as they come in, the gravitational potential energy, we're still talking about this GPE stuff, guys, all the way since the beginning of last year. Gravitational potential energy is going to decrease, right? Because they start to come together. Now, if gravitational potential energy decreases, the kinetic energy is going to increase. And we know that kinetic energy is proportional to the temperature. So if the gravitational potential energy is going down, kinetic energy is going up, that means the temperature must be going up. So as these gas particles start to fall in towards each other, they get hotter and hotter and hotter. If they get hot enough, then they start the fusion process, and the hydrogen starts to fuse into helium by the process that we talked about before. If you don't remember that process, go back and look at it again. At that point, we didn't really have a reason to feel like we needed it, but now we've talked about it a couple of times. Make sure that you know that process, the basic idea of how the helium turns into various atoms and various molecules as it turns into that helium. All right? Now, that's the birth of a star. That's how it begins. What we want to talk about now is what happens when a star dies. Okay? What happens when a star dies? Well, we've talked about this a little bit too, right? We talked about the sun. Let's take a star. Now we're talking about stars that are about the size of the sun. Maybe up to, 4 times the mass of the sun. Okay? Not anything too big, but within that idea. Okay? So these are small stars, okay? Small to normal sized stars, okay? We talked about the fact that as we start to use up the hydrogen, right? We've got this hydrogen to helium fusion. So as that hydrogen starts to run out, it starts to cool off, right? It starts to collapse. As it starts to collapse, it heats up, which then means that the outer layers can start burning, right? That's where we get into this red giant phase, okay? This goes for a very, very long time, right? So we talked about the sun before, okay? We're maybe 4.5 billion years into the life of the sun right now, okay? It should be able to do that for about 12 billion years, okay? So we're almost halfway, all right? Now, after this, we start to get into a point where it turns into a red giant, right? We've talked about that. After it's a red giant, right, it starts to generate enough heat that now the helium can start to fuse. It's not just the hydrogen anymore, it's the helium as well, right? Now initially, it's going to collapse, okay, but as the helium starts to burn, we get what's called the helium flash. And the helium flash is when the helium starts burning, and all of a sudden there's a whole lot more energy, and it's going to push it out into a much, much larger star again. All right? And so now we have this larger star. At this point, if it's a normal size, normal sun size, at this point, it's not going to get any bigger. It's just going to burn and burn and burn. Okay? It is going to get hotter as we start to burn the helium and some of those other elements, but at this point it's not getting any bigger. It's just going to keep getting smaller and smaller and smaller as we use up those atoms, and then eventually it's going to stop burning so bright. It will still be very, very hot, but it's going to be pretty small now, right? That's why the luminosity is so low, is because it's actually much, much smaller at this point than it used to be. Okay? So that's over again billions of years that it starts to slow away. Some of the outer layers, right? You've got, remember the supergiant, the giant is because the outer layers of the star are burning. At some point, these guys are going to start to kind of float away, push away because of the degeneration pressure of the helium inside that's burning. You're going to start to get some, sorry, I said degeneration, I meant radiation pressure, is going to push some of those out, giving us a planetary nebula. Over billions of years, it is going to cool off, and then we'll talk about what's going to happen to it after that in just a little bit. There we go. Can you see the white dwarf? There's lots of white dwarfs. We said 9%. So almost 1/10 of the stars in our universe is white dwarfs. But it's not this one. That one's big. Here's your white dwarf. Right there. Okay? It's very, very small. Right? And it's blue, right? It's over on that high spectrum because it is very, very hot. But because it's so small, it's not very luminous. Okay? Very small size, though very bright. This one, this is actually Sirius right here. Okay, this is Sirius A. Sirius A is actually the brightest star, the highest apparent brightness in our sky. As far as we can tell, that's the brightest star. This is Sirius B, which is a white dwarf. They are a binary star system. They are revolving around each other. We can tell by the way that they move and their wobble as they move through the sky. So anyway, it's interesting to note that this guy right here, Sirius B, it has the same mass as the sun, but its size is about the same size as the Earth. Right? You learned back in like 4th or 5th grade how large the sun is compared to the Earth. Well, think about if all the mass of the sun got crammed into the Earth. That is a white dwarf. That's pretty cool. All right, that's what I'm going to finish with today. We'll pick up with this a little bit later, but for now I think this is enough to get you moving on some more of those problems. All right, thanks a bunch.